I'm going to start my today's session, and I'm going to start from the point at which I continued till my last class. And so far as I can remember, that we were discussing the probability distribution for a discrete random variable. And you know that if we have a random variable capital X and its corresponding probability is represented by P of capital X is equal to small x, where small x are individual outcomes which the random variable can take at different points of time, then such a chart is called probability distribution chart. And if the sample space from which the random variable X is taking the value is finite or countably infinite, then we call capital X to be discrete random variable. And hence the probability distribution subsequently is known as discrete probability distribution. And we also learned two properties of the discrete random variable, of the probabilities associated to the discrete probability distribution. One property is very simple. It's directly coming from the axiom. It is probability of X equal to X, which is always greater than or equal to 0. And if you consider probability of X equal to small x for all possible values of X, this is equal to 1. Not only this, we also discussed the quantity which is called Ex, which is denoted by Ex and is called the expectation of X. And it is calculated for discrete random variable case. It is calculated by multiplying each of the outcomes by its respective probability, and we can sum it up over all possible outcomes. Okay, so this much we discussed in our previous class, and the example that I considered, I'm rewriting the example once again. It is, we considered a coin tossing problem where the random variable came out to be having these 5 values, and the corresponding probabilities were 1 by 16, 4 by 16, 6 by 16, 4 by 16, and 1 by 16. Now, the beauty of this chart is that suppose you want to declare that this is your probability distribution chart for the coin tossing problem. If you declare this, anybody who has the basic knowledge of probability distribution can test whether your chart is complete or not. If he finds that the total of these probabilities starting from 1 by 16 to 1 by 16, if the total of this item is equal to 1, then your chart is complete. And if it is not, then your chart is not complete. That means probably some values you haven't considered. So this particular property can also be considered to be a checking criteria to test whether a discrete distribution is complete in its content or not. Now, I will ask all of you, those actually who are attentively doing my class, you know, you have got the formula for E of X. Now I will ask all of you to calculate E of X for this particular chart. So your next job is to find out what is the expectation value of this random variable for the coin tossing problem. So do it quickly and write the value in the chat box. You can write the value if it comes in fraction, you can give me the result in fraction, or you can write the result in decimal point also. So just quickly calculate the expectation. What you need to do is that you have to multiply the values by its corresponding probabilities. So 0 will be multiplied by 1 by 16, 1 will be multiplied by 4 by 16 plus 2 will be multiplied by 6 by 16. 3 will be multiplied by 4 by 16 and 4 will be multiplied by 1 by 16. Okay, so what is the value coming? The value that is coming for this particular problem is, someone has written in the chat box, it is 10 by 16. Okay, so the value is 10 by 16. Is it 10 by 16? Is it correct? It is not 10 by 16. As I can see, 2 into 6, that is 12. 3 into 4, that is 12. 12 plus 12, that is 24. 24 plus 8, that is 32. So the expectation is 2. Yes, expectation is 2. Now, so we have come across, and we also know that this expectation formula is actually, by expectation, we actually understand that we are actually calculating the average of the random variable capital X. And I also told you that why it is so, because to calculate average for a frequency distribution, we consider this particular formula where the value is multiplied by the frequency. Here, the difference is that instead of taking frequency, we are considering the probabilities. Okay, this was the formula calculating average, but here the denominator term will not be there because total probability is always equal to 1. So from this particular formula, we can correspond the formula of expectation in the following manner. Now we have also come across in our school days that whenever a particular distribution is there, distribution of points are there, here and there lying, we always try to find out a kind of unique number which will give us a tendency of the chart of values that will be scattered around this particular point. Okay, so in a word, if we can find out that unique value from the distribution of points, then that unique value will reflect how the system is behaving. Say, for example, if the student has set for a particular examination, and if I have in my class 60 students and I'm getting 60 different marks, suppose the system is so unbiased, the students are not copying, so obviously 60 different marks I am expecting to get. Sometimes it may so happen that some terms are very some marks are similar, because suppose the performance of the students are same. So it may so happen, but if I am given all the 60 marks, I will not be able to say anything about the distribution, because it becomes not very easy for me to declare how the system is behaving, means how my students are actually performing. Because then in that particular case, I have to look at each and every point, and then I have to claim something. But it is far better if we can find out a pillar which will reflect the entire distribution. And that pillar, suppose this is the point which I'm concerned with, and this is the point for this particular chart that I have considered. Suppose this point is 2. So what this means? This means it is the central tendency of the distribution. This is the central tendency of the distribution, and all the other points are actually scattered around this particular central tendency. Some points are more than that and some points are less than that. So this becomes our benchmark. But at the same time, we also are interested in finding how much the points, other points, are scattered from this particular central tendency. Okay, how the points are scattered from this particular unique value, which in my case it is the expectation. So we are actually interested in finding this distance of these points from this unique number. Okay, and we know that there are various measurements by which this particular thing can be calculated. One of the measurements is called variance. It is called variance. And we also know that if we can calculate the variance of the distribution, and if we take the positive square root of variance, we get another quantity which is termed as standard deviation, which is called standard deviation. Why do we take the positive square root? Why not the negative square root? Suppose my variance is 4. Suppose my variance comes out to be 4. Then we actually know mathematically that root over 4 is plus minus 2. But here, minus 2 will not be the variance. Is not, sorry, the minus 2 will not be the standard deviation. Plus 2 is the standard deviation. Why is it so? Because since standard deviation is actually the measurement of distances of the other points from the central tendency, distances cannot be negative. So we only consider the positive square root of the variance. So this is the quantity which we are not going to consider. Remember this particular fact. Now, variance in statistics is a very important quantity, and it is actually a measurement of dispersion. Dispersion means how dispersion is synonymous with the term called deviation. So that means how the values of the chart are scattered, deviated from a given point. So whenever we have a probability distribution, we also become very much interested in finding the variance of the random variable. We have calculated the expectation of the random variable. That means the mean. Now we want to find the variance of the random variable capital X of our coin tossing problem. So we need a operational formula by which this variance can be calculated, and that operational formula is given by variance of the random variable capital X, which we actually denote by V of X, is given by the formula E of X square minus E of X whole square. This I personally call it as an operational formula, okay, because it is actually easy to use, easy to apply. But the definition of variance, if you go with the definition, it has another formula which is sometimes used, is given by this E of X minus EX whole square. Okay. Now, if you say that, okay, what is the connection of this particular formula with the actual variance that we have learned in statistics, then you will see that for a frequency distribution, variance is actually calculated by the formula, which is summation Fi into Xi minus X bar whole square, and we divide it by total frequency. If you can recall, this was the actual formula of variance. Now, what we do is that from pedagogical point of view, I am just saying, okay, suppose this quantity I am considering as my operator capital E. This quantity is the operator capital E. In place of 1 by n summation Fi, I am considering operator E. And then I'm putting the bracket. In place of this quantity, X, I'm putting the random variable capital X, and in place of X bar, but you know that expectation is nothing but equal to X bar because it is the average. So in place of X bar, I'm writing E of X. I'm writing E of X. Okay. And I'm putting the difference sign minus and just taking the square of this. So you just see that these two things are actually very, very much equivalent to one another. You can, if you forget the formula, you can think of this original formula of the variance and you can accordingly deduce it. Another operational formula for variance is given by this 1 by n summation Fi Xi square minus X bar square. From there also, you will be able to find out the operational formula of the variance in terms of expectation. Let's see. So in place of 1 by n summation Fi, you are going to put expectation E. In place of Xi, you are going to put capital X. So it will be X square. And you know that X bar is nothing but EX. So in place of X bar, I am going to put EX, and that will be squared. Okay. So you see both of these formula actually have very much similarity with the formula that we worked in our school days. Okay. And actually, you know that this is the formula that you have come across in terms of expectation is the actual formula. Other formulas are the, corollaries of the original one. So we have got our operational formula for calculating the variance. The problem is this. Now, if I ask you to calculate the variance of this random variable capital X, you will immediately ask me one question that you have told us that we can calculate EX by multiplying the values by the respective probabilities. How am I supposed to calculate E of X square? Okay, so to answer this question, I must say that there is a general formula that you have to keep in mind, that if capital X is any random variable, and if I multiply X with itself n number of times, where n is a positive number, remember n is a positive number, n is positive, then this is given by a formula, which is summation over x to the power n, probability of x equal to small x. So this is how we actually calculate the quantity E of x to the power n. We can apply this particular formula to calculate E of x square. So I'm going to the next page. So now we have E of x square. So according to our formula, we are going to take the summation of over all possible values of x, and we are going to take the square of x, and that square will be multiplied by the corresponding probability taken from the chart. Now we have the chart with us. So if I want to calculate for our chart, if I want to calculate the expectation of x square, it will be like this: 0 square multiplied by 1 by 16 plus 1 square multiplied by 4 by 16 plus 2 square multiplied by 6 by 16 plus 3 square multiplied by 4 by 16 plus 4 square multiplied by 1 by 16. So now your job is to calculate this value, find out this value, and then you substitute the value in the given formula that I have explained in the previous page. So we have the variance formula E of x square minus EX whole square. I told you that this is the operational formula because most of the time I will be using this formula. So here you are going to substitute this value E of x square, and you have already calculated the expectation of the random variable. So put the value, which is 2, and take the square of this. Now you are going to calculate this variance quickly, and you are going to write in the chat box. You can directly message me through the chat box and tell me what value you are getting. It's a quick calculation. So I'm waiting for your reply. $21 is the, okay, someone has written, yeah, Moinak has written the variant expectation of x squared is 5. Okay, Moinak, it is 5. And thus, what is the variance of x? It is 5 minus 2 square, that is 5 minus 4, that is 1. So for our case, the expectation of x is 1 and the 2, and the expectation of x squared is 5. So the variance of this quantity is 1. Variance of this quantity is 1. So all the points 0, 1, 2. Now it is very amazing to know. No problem, no problem. If someone has written to me in direct message that he is feeling sorry that he has given me the wrong reply, the calculation may be wrong. In my last class, I did a wrong calculation, and you have corrected me. One of the students made a comment on on one of my videos and said, "Sir, you did it wrong." So I also sometimes, to err is human. Then there is nothing shame in this. Okay, you can do the wrong calculation. You don't have to be sorry for this. Be careful so that shouldn't do the mistakes. Now you see this one, when this one is coming, it is very amazing to see that what sort of random variable we started working with. Our random variable was of this form 0, 1, 2, 3, 4. And you see every point, this point is 1 unit distance apart from this. And what was the mean? The mean was 2. So suppose this distance, the distance of 0 from 2 is actually 2 units. Now distance of 1 from 2 is 1 unit. Distance of 2 from 2 is 0 unit. Distance of 3 from 2 is 1 unit. Distance of 4 from 2 is 1 unit. Now you are going to calculate and find out the average distance. It will be approximately equal to 1. Okay, so this is the thing by which actually we calculate the this is why we actually calculate the variance of the random variable. Now remember that this topic of expectation and variance is so important that in my subsequent lectures I'll often utter their names from time to time for various other scenarios. Okay, so this much also for this given example. I'm again copying the example on this in this page, the chart on which I actually calculated expectation and variance, because the discussion on this particular problem is not yet complete. I'm going to talk about something else very interesting. So I'm rewriting the chart. So it is 1 by 16, 4 by 16, and 6 by 16, and 4 by 16, and 1 by 16. Okay. Now, for this particular problem, we have calculated expectation, we have calculated variance. We want to further analyze the given probabilities. Now, when we look at these probabilities, we are thinking, can I give a kind of formula to the probability of x equal to small x? We know that this is actually called the probability mass function for discrete case. Okay, so in short, I'm calling it PMF. So my next objective is to give a kind of general formula to this particular probability. So if I think a little bit, you will see that we can give a general formula like 4cx by 16 to this probability mass function. To this probability mass function, where x is taking values from 0, 1, 2, 3, 4. Now see, 4c0 is 1, so we get 1 by 16. 4c1 is 4, so we get 4 by 16. 4c2 is 6, so we are getting 6 by 16. 4c3 is same as 4c1, so we are getting 4 by 16. 4c4 is same as 4c0, so it is 1 by 16. So actually we are able to find out a formula, general formula for this particular probability. What is the, why am I doing this? Okay, let's dissect this particular formula once again. Let us dissect this formula. Our next job is to dissect the given formula and see what comes out of it. Probably you have not looked at probability from this type of perspectives. So now you see that what I'm going to do. What was my problem? My problem was actually a coin tossing problem. Okay, my problem was a coin tossing problem. Very good, very fine. And how many times I actually tossed the coin? How many times the coins were tossed? The coins were tossed 4 times. The coins were tossed. Okay. How many times the coins were tossed? Not someone has written that 16 in I didn't toss the coin 16 times. I tossed the coin 4 times, and the total number of possible outcomes was actually 16. because remember this fact that simultaneous tossing of four coins is similar to the fact one coin tossed four times, and total number of outcomes thus contained 2 to the power 4, that is 16 items. Okay, but I didn't toss the coin 16 times. This is the number of possible outcomes that can come while tossing a coin subsequently 4 times, or by taking 4 coins and simultaneously tossing the coins one at a time. Okay, so how many times, this is the point number 1, how many times I toss the coin? I toss the coin 4 times. Point number 2 is that, okay, we considered the coin or coins to be fair or unbiased. Okay, that is point number 2. And we also considered each throw of the coin is independent of one another. These are the conditions that we actually applied over here. Okay, now, so by keeping in mind this condition, if I now say that, okay, we have a coin, one of the face is H and its other face is tail. Suppose we are tossing the coin, we are tossing this fair coin only one time, and since it is fair, we all know that probability of H will be equal to half and probability of tail will be equal to half, and indeed probability of H is equal to 1 minus probability of tail. We all know this fact. Okay, and since we have considered the coins to be in so the experiment to be the independent trials to be independent of one another, so if we get an outcome like probability of H, which is actually nothing but probability of H intersection H intersection H intersection H, then by the theorem of independent probability, we know that each of the probabilities will be actually multiplied. Okay, and thus you can see that we will get 1 by half to the power 4, which is 1 by 16. And in this manner, we actually calculated all our probabilities corresponding to each and every outcome. We are only able to do so because we assume that the coins are fair and the trials are independent of one another. Now, here comes the most important part. We have got our formula to be 4cx 1 by 16. Okay, we are going to dissect the formula in the following manner, and you see that if anything changes or not. If I try to write the formula in this manner, 4cx half to the power x half to the power 4 minus x, I think there will be no problem, because this is similar to 4cx half to the power 4, and that is 4cx by 16. So we have dissected the formula in the following manner. Now let us try to find out what are the individual terms here. This term 4 is actually the number of trials that I have made. This term x is the favorable outcome that we want or that is coming, or favorable outcomes that may come. What is this head half? we can consider this to be probability of H. What is this half? We can consider this to be probability of tail. So ultimately what we have got now for a coin tossing problem or for any problem in general, if we say that for an experiment, capital S is the success. And in my case, this success I'm considering to be getting head. For some other people, it may be getting tail also. There is no hard and fast rule. And corresponding to each success, there will be a failure always associated. And in my case, it is getting tail, say for example. Okay. And for individual tossing, if I assume for one such experiment, if we assume probability of S to be small p and probability of F to be small q, so that small p plus small q is equal to 1. If it is so, then we can give a general formula, a general picture to the given special case. We can consider this to be our special case. This is our special case. So we can give a general formula to this. So let's see what is the general formula coming. The general formula coming is the following manner. General formula coming in the following manner. If we consider the number of experiment to be n, number of experiment to be small n, then the general formula will be ncx p to the power x q to the power n minus x. Try to correlate this formula with the given formula. And we are considering this constraint that p plus q equal to 1, and x is taking value from 0, 1, 2, ... up to n, where x equal to 0 means no success, x equal to n means all successes. Okay, so x equal to 0 means no success, and x equal to n, and in this manner x equal to n is all successes. Okay, so we are able to give a general formula of this kind, of this type of situation. Why am I doing so? Why am I so interested about this general formula? It is because, okay, but let us say something else before. And meanwhile, the time is running out, so you are supposed to write your roll numbers in the chat box. Okay, please write your roll numbers in the chat box. So we can now say that we can now give a definition of what we have done so far. We can say that if for a discrete random variable, capital X, if the probability mass function is given by the formula, probability of X is equal to small x, which is ncx p to the power x q to the power n minus x, where p plus q is equal to 1 and x is taking value from 0, 1, 2 up to n, and 0 otherwise. That means whenever we write 0 otherwise, it means that if small x is taking value 0, it is not taking any other value. If small x is taking value n, it is not taking any other value. If it is taking n, then all value has been considered. So if a random variable has this sort of probability distribution, we call this random variable, we call such a random variable x to have a special type of probability distribution, which is called to have binomial distribution, because said to have binomial distribution, or is said to follow binomial probability law. Binomial probability law. So this binomial probability distribution is a kind of discrete probability distribution whose probability mass function is given by this particular formula. Why it is called binomial probability distribution? Binomial distribution is because if we consider the term p plus p and q, and if I expand it with the binomial theorem, okay, in this manner, its general term will be given by this formula. And lastly, we are going to get q to the power n. This is the general term, and since this is the general term of a binomial theorem, so this type of distribution is called the binomial distribution. And in this case, the trials, those trials which are independent, they are actually called, as a special name, they are actually called Bernoulli trials. Bernoulli trials. Now, I am saving the only 40 participants I can see, but only 39 people have responded in the chat box. If someone is not writing in the chat box, that means his attendance will be missed. This is not my responsibility. Probably he has opened the link and he is sleeping, so tired. Now, okay. Now this much I'm actually discussing in this particular session. After the session ends, you again rejoin. After the session ends, you again rejoin for at least 10 minutes. And I have to summarize that what I have discussed. Okay, so I'm stopping here right now. Please join in the next session so that I can summarize my today's discussion.